My name is Will Godsey. I'm on the Salmon team, and my teammates are Glenn Garrett and Stuart Wheeler, and we have the duck cooling station. Today I'm going to talk about the steady state operating curve, the step input response, and the FOPDT diagrams. Here's a setup of the cooling station, and right here is a blower. Blows air through these ducts, and there's a temperature sensor right here, and there's also one on up here, which feeds us the outputs. Here's a block diagram of steady state operating curve. We have the manipulated variable, which is the power input, and that's fed into the system, and then the system puts out a control variable, which is the output temperature. And the ranges for all of our experiments was Glenn had 50 to 52 degrees Celsius, I had 52 to 54 degrees Celsius, and Stuart had 54 to 56 degrees Celsius. Here's an example of our steady state operating curve. And for this one, our input was 50%. And then what we did, we analyzed a little section right here where it was steady state, and we found that the average temperature was 53 degrees. In that state, it was 53 degrees. Here is a graph of all of our results compiled together, and you can see that our ranges were from 50 degrees to 56 degrees, so that was good. And the trend line equation was basically -2 times the input plus 151. And the reason why it's negative is because as the input values increased, the temperature drops. And then for the step response, here's another block diagram, and it's basically the same as what it was before. The step input is put into the system puts out the output in degrees Celsius. And we were looking for the gain, the dead time, and the time constant. And here's an example of how to find the gain. You can see on this graph that the range is from 50 to 75%, and then the output range was 7 degrees. So you take the change in the output over the change of the input, and you get a gain of 0.28 degrees Celsius. And for the dead time, you do a best fit line of this slope right here, and it intersected with where the step up was, so our dead time was 0. And then here's how you find the time constant. You do 63.2% times the change in output, which we found earlier, and you get 4.4 degrees. And so you go down here and make a horizontal line from up here, and where it crosses, it gives you this gap, and that gap is about 0.4 minutes, and that was our time constant. And this is a graph of our averages for the entire experiment. Our results weren't as good as expected because a lot of people was trying to run stuff, so the system got backed up. So as you can see, the lower range, or the step down, was a lot higher than the step up. And the dead time, basically 0. You can see the chart goes from 0 to basically 0.05 seconds. And then here's of the time constant. Again, just like the gain, the step downs were a lot higher than the step ups. Here's a little bit of background on the FOPDT. FOPDT is actually first order plus dead time. Here's the equation that we use for the model. And in this, we were looking for the gain and the time constant and the dead time. And there were two methods of going about this: the graphical method, or the alternative method, which was the trapezoid rule, which we learned about in computations class. Here's an example of one of the graphs that we did for the step up. You can see that the input model and the actual input were virtually the same, and the graph actually matches pretty well once it hits the step down, or the step up, I mean. then here's another example of the step down, and same thing, the inputs overlap, and then the curve is fairly similar on after it hits the step. And comparing the graphical to the alternative method, you can see that everything was pretty much the same. The dead time was basically 0, and the gains were a little off right here, but they were a little bit closer on the step down, and also the tau, or the time constant, was closer on the step down than the step up.